Hello, so welcome back. We have done the first part, geometry and meshing. If you are new to this video, you can go and watch how to create a geometry and meshing. So for doing the simulation setup, yeah, we need mesh and the boundary condition. Actually, these are important. For this, I have boundary condition for the vertical upward. There is a experimental case for, like, we need the velocity magnitude for the air and water for the first primary phase and the secondary phase, and the volume fraction and the interfacial area concentration. Because interfacial area concentration, why I needed, I am applying here to interfacial area transport equation model. So let's move there, and we have done the geometry and meshing. Transfer this data to new Fluent. Okay, the mesh is imported there, and make sure to, for the solver option, type the double precision and how many processor or the parallel machine you have. So currently for my laptop it has a 20 processor. Okay, so open the Fluent and we will do the settings one by one. Okay, maybe the text size is too big. Let me adjust the display setting. Fine now. Okay, so first step, when you open the Fluent, is you need to check the unit, because we use unit everywhere. Okay, check the mesh if there is any negative volume. No. Okay, display the all visible inlet, outlet, boundary and everything. Okay, so for the gravity it's always pointed downward, so 9.8 in y direction is fine actually. So we have done in the general setting. In the general tab we do mostly these settings, and yeah, after that, now the second, here in the setup, the second is the models. Okay, so here is the two-phase flow simulation. We will on the multi-phase simulation. For the multi-phase simulation, there are for the homogeneous model, there are three model available, and the inhomogeneous, there is only one Lurian. So we want to apply the Lurian model, and we use the volume fraction parameter as implicit. Okay, let's apply the Lurian model, multi-phase model, and yeah, let's just give a few seconds. Okay, so the Lurian multi-phase model is enabled. Now we want to specify which phase is the first phase, primary phase, and the secondary phase. But before this, we need to add the material. By default, it's only the air. In the fluid region, by default, it's only the air. In the Fluent database, go and there add the water as liquid. Copy parameter, close, and now it's close. We have two material in the fluid section, air and water. Then come back here, and yeah, your primary phase will be the continuous phase, that is water liquid. Okay, and your secondary phase, yeah, secondary phase will be the air. Okay, so we want to apply the interfacial area concentration model. That's why we will check the interfacial area concentration. Okay, so here are the option, what what you want to specify: the starter mean diameter, user defined function, constant, starter mean diameter from 1.5 to 2.7. These are actually you can get from the experimental data, and these are your boundary condition actually also. So for the interfacial area concentration, there are the breakage and the coalescence kernel. Basically, interfacial area concentration model dynamically, it's actually predict the changes with the passage of time, with the flow, how the bubble breakup and coalescence. On these two mechanism it works. So for the breakage kernel, there are a lot of model available. You can select anyone you want, so which is best for your simulation, your model. And after selecting the faces, and now we will go to the phase interaction. For the phase interaction, first of all you need to give the surface tension. It's, actually it's by default 7.0728. And surface tension force modeling, you need to apply it, continuum surface force, whatever your simulation needs. Virtual mass coefficient is normally 0.5. okay, you can leave it as a default what you want. Okay, so for the drag coefficient, you can choose, there are a lot of models available. You can choose what your simulation actually needs. Okay, for the drag modification, if you want a drag modification, if your simulation needs, you can apply it, otherwise you can leave it as a none. For the lift force coefficient, there are 5 models available. So it actually really depend on your simulation boundary condition. So I'm going to apply for the simulation Tomiyama, and like for this also, it also depend on your boundary condition what coefficient you need, but you can leave as default. It doesn't matter, like for this first simulation. So otherwise you can select what I am selecting, that will be okay. Okay, so we have done the phase interaction, phases, but basically these are called the interfacial forces. So here we have done the multi-phase modeling, Illyrian with the interfacial area concentration model, and here we specify the phase and the interfacial forces. So our next step is the viscous model. So by default it will the k omega. It's up to you what you want. So currently for me I want a k epsilon, so standard k epsilon method, and the near wall treatment, the wall function, I am using the enhanced wall treatment. So actually this is a dispersed phase, this is not a mixture because the air volume fraction is too low. Okay, so you can also check this if you don't want that, it will not affect your results actually. So the first step is check in the general tab, check the mesh and display, and specify the gravity, and the second step is the specify the multi-phase model, and third step is to specify the viscous model. So we have done this, and we have added the material in the setup. These things are done. Okay, so now is the most important thing, that is the boundary condition. So inlet boundary is basically the velocity inlet. Okay, for the mixture you can leave, for the pressure you can leave it as a 0, you can run at constant pressure. For the phase 1, okay, from the boundary condition you can see we have the boundary condition here, and the velocity magnitude, actually that is a superficial velocity. If you convert it to velocity magnitude, it would be the 4.1. okay, for the phase 2 momentum, first in the momentum section, that the velocity will be the 4.179. okay, from the superficial velocity you can convert in, if you know the bubble wide weighted bubble velocity, you will put there for the two-phase flow simulation. Basically, we don't use the from the superficial velocity, the velocity magnitude. Okay, with the time when you read the theory, you will understand why we need the velocity bubble wide weighted bubble velocity as a velocity magnitude as the inlet condition. Okay, so in the multi-phase section, you need to specify the interfacial area concentration and volume fraction. So the volume fraction is 0.243 and that is here actually 86.46 interfacial area concentration. Okay, so now we have specified the boundary condition at inlet for the primary phase and the secondary phase. Okay, so internal, it should be the fluid internal. Okay, for the outlet. Okay, sometimes your pressure prediction is not similar with the experiment, so you can put pressure at outlet boundary and then it will predict the inlet pressure after getting the pressure drop. So it's up to you. You can like you can run it with the constant pressure also. It's okay, but it's depend on your case. If you have some pressure at in the experimental data at outlet, then yeah, you need to be consistent with the experiment. Okay, for this case actually to be consistent with the experimental data by hit and trial method, we need to put this pressure, but you can leave it 0. It will not it's not really important for the simulation. But if you want to be consistent with, if you want to really match your results with the experiment, then yeah, you should know this. Okay, apply there, and that is for the mixture. Okay, phase 1, nothing to do with this. You can backflow turbulent insensate, should leave at 0, 0. Okay, for phase 2, you can put the inlet condition as boundary condition as at inlet, backflow volume fraction 0.043. That's fine actually. Okay, so boundary condition is done. So, and next is the solution methods. So you can use, there are two options: phase coupled simple and coupled. Well, mostly it's recommended coupled, but actually it's run with high under relaxation factor and sometimes the results are not good. It's depend on case. The complex case, we should run the phase couple simple. Okay, for the pressure, the discretization scheme, we use Presto, that's fine. For the momentum, you can choose as a second order upwind or you can choose as a quick. So the first order, then second order, and then quick, then third order. It's follow this order. So if you want high accuracy, yeah, you can choose the higher order, but it will take more time in convergence. So if you're running with a very fine mesh, it will take maybe days to complete the simulation. So it's up to you what level of accuracy you want and how fine is your mesh, how big the resolution. Okay, but second order is fine. For the volume fraction, mostly cased in, they are highly unstable. They don't work with the higher order like modified HRIC and high resolution image capturing, actually HRSIC mean. So obviously that is better than the first order, and also quick is better than the modified HRC. But for the initial simulation, it's fine actually, you can do this. For the turbulent kinetic energy, you can use quick third order, so it will not affect your results more. The volume fraction and the interfacial area concentration discretization scheme will affect your results more, because I have checked for this case. If we run with the higher order for the volume fraction, the case will be highly unstable. So if we want it run it in the stable condition, we should run with the first order. Okay, so we can use quick for the interfacial area concentration is now done with this. So in the control tab, that is actually the under relaxation factor. By default you can see the pressure is 0.3 for almost every case. Momentum and volume fraction, here you can see these are the default, but there are some cases like for this case, that is a special case actually, that is highly unstable. Although every vertical upward case is unstable, because the phase distribution is not uniform here, so that's why they required for the phase couple simple method also it's required a lower under relaxation factor. So you can run with the default under relaxation factor, but there will be problem. So you can down it, you can like reduce the under relaxation factor up to, even you can put 0.1 here. So under relaxation factor will just reduce your convergence time. It will not affect your results as much. It might affect, but once you get the convergence, it will not affect. Okay, we will run with the default under relaxation factor, but these are really important. So for the reports and definition, what type of reports you want to generate? Okay, mostly we want a surface report with the area weighted average. Okay, so first we want to like see the volume fraction. Okay, so mostly in that case we usually check the results at different height, like for this case that is 3-meter long pipe. So first report we want to check at a height of 1.7 meter. For this we will create a plane first, actually the ZX plane. Okay, we want to check at actually we have an experimental data at this point, so we will create this plane, and this plane is called 34D. Okay, now this plane is created, and we also want another plane 61D, and that is size for 7. Okay, so we have actually that is ZX plane. So these planes are created, so now we can generate the report. First, usually we need the area weighted average of void fraction. Okay, void at 34. Report file, no, but you can check the report plot. Here it's by default field variable. We want phase, actually the volume fraction, basically that is the void fraction of phase 2 at what, at plane 34. Click OK. So we have this report. We also want the surface area weighted average report of interfacial area concentration. Okay, at 34D. Uncheck the report file, we don't want this. And here in the field variable interfacial area concentration at 0.3, 34D. Okay, and yeah, we also want the velocity. We want to check the velocity at 34D. Okay, velocity of mostly we check the velocity of phase, every properties of phase 2, because phase 1 is continuous phase. Okay, and then we want a flux actually. So we want a mass flux, we want to see how our convergence is ongoing. So mass flux inlet, basically the difference between inlet and outlet, we also want to check this. Okay, you can name that as a mass flux. Okay, so we also for actually that depend on every case, on different case, but for this we want to specify the pressure also, because we have specified the pressure at outlet. We want to see how much pressure drop is going on and what is the pressure prediction at the inlet. Static, we want the absolute pressure of the mixture where at inlet boundary. So here we can specify. So I have specified some of the parameters at 34 D. It depends how many axial location you want to specify, you want to see your results. So you can specify all the 61D also is on your. Okay, so there is another method, like if your simulation is running, you can see your results from the control plots during simulation. That is actually a trick, a shortcut to see your results, how it is going. For this, yeah, you need to create a control plots. Okay, here okay, so monitor, we can do this later, but first we need to specify the convergence criteria. Okay, by default it's 10 raised to power minus 3 for the normalized equation, that is residual actually. So it's depend on your case. Normally we need 10 raised to minus 4, but by default it's 10 raised to minus 3. I will leave that as a default. There is another criteria, like if your mass flux, the difference between the mass flux, it should be the 0.01%. Okay, we have specified the mass flux report, we can see in the results when the simulation will be running. Okay, so convergence condition, we have specified the convergence condition. We don't need the cell registered right now. And go to the initialization. You can choose the hybrid initialization and the standard initialization. You should start with the inlet. It's up to you. It actually doesn't matter really, but you can specify. Okay, so like I said, we sometimes we want to see our results when simulation is running. So create a new, and I want the control plot of of wide at 34D. Okay, control plot, I want to see the volume fraction of phase 2 at 34.5D, and click save and display. Okay, but actually by default it doesn't show the right view, so we can easily adjust the window. Okay, we can do it later. We also want to add the second location also, wide at 61D. Basically, with the passage of time, with the every iteration, you can capture the convergence process. That is really important actually. So when you will do more work here, and you will understand, yeah, it's really actually important. So save and display here. plane 61D. It's actually showing here. Okay, so we have specified the control plots here, and now we want in the calculation activities. In the calculation activities, autosave, like if you have run the simulation and you want to save your results at every like 1000 iteration, you can put like you don't need to stop the simulation. Fluent solver automatically save your results after every 1000 iteration, what iteration you specified here. Each time, if it can save your case file also if you modified it, or every time, it's up to you. The case file is different and the data file is different. Basically, it data file contain your all simulation information. Okay, so it's up to you. For this case, I don't need actually, so I will not specify. But if you are running, well, like if you want to run for one day, but if you are not sure whether it sometime laptop may stop working or power shut down, so it's better to save the data file auto. Then you can rest assured it will not, you will not, your time will not be wasted. And the next option is solution animation. Actually, solution animation is that you can capture the convergence process, like how after every iteration how your phase is ongoing, like the volume fraction. Basically, in two-phase flow we capture the volume fraction, how it is going through, like where the bubbles are moving, migrating towards the center, towards the wall, and yeah, how they are moving. So this is important. So we can save as animation one, like I'm first I want to capture the animation at 34D. Okay, you can save HS file or the PNG or JPG, EMG. Okay, so we want to check record every after every 10 iteration, where first I need to check the void fraction at this. Okay, so now okay, so it is like the how it will be shown when it will capture. So you can adjust this window. It will be, I don't know why it is not. Mhm. Okay, now it's working. Okay, so let me adjust it. Okay, animation at 34D. Okay, I use this active window. Okay, I want to save as a PNG image. Oh, okay, after every 10. Okay, so it will automatically actually save because the case file is already saved. uh, okay, here, and now for animation at 64, also want this the PNG image after 10 iteration. Also I want this for the 64D. Okay, first we need to adjust the window because it will capture as it is showing now, so it's important to adjust the window. Okay, uh, okay, you can adjust this. Very good. Okay, use this active window. Now it's done actually. So everything, the simulation setup is done. Now we can specify the number of iteration. Let's suppose we give it 300 iteration and do it, run the calculation. Okay, so it's running the simulation now. It will take time. The simulation is not started yet. It will just take time to start. It also depend on your how much is the computing power of your processor and how fine is your mesh and number of elements. Okay, the simulation is not started yet. It will just start in few seconds. So now our simulation is started. Okay, so we have actually specified the interfacial area concentration at 34D, and then the volume fraction, area weighted average velocity, the mass flux. You can see how the mass flux is changing and the pressure, and we have also specified the control plot. So you can see here how the convergence is ongoing after every 10 iteration. You can see at every iteration with the change of every iteration at 34 point D. And yeah, that is a broader view from the control plots. You can see how the simulation is ongoing. Actually this will be saved in as an image. So you can see now the bubble are moving towards the center. Yeah, that is actually the volume fraction of phase 2, how it is changing in the pipe, in the round pipe. Okay, you can see it will be changed. Here you can see the value also where the volume fraction is going. Okay, here you can see that is actually the simulation. Once the convergence will be done, then we will check the results, the local results and the global results in the post processing. But with the passage, with the experience, you can also check your results with this contour plot also. Yeah, actually it will take time for you to understand this one also. So the simulation is running, and once the simulation will be completed, we will check the results in the post processing. Okay, leave that simulation. You can check here each and every results, how is it going. But actually this will be with the experience, you can check the results and you can